Okay, so it's going to be recorded. If ever I know some people couldn't get here, so that's it. All right, so we're doing this tutorial on inner product, right? First, maybe you have questions about the lesson. Okay, so it's really related to what we did. It's really an extension as all of what we're doing this semester on linear algebra, an extension of what we did on matrices during first semester. Okay, so during first semester we dealt with orthogonality, orthogonal projection. So we're going to talk about orthogonal projection in the next class, but in a broader sense of vector space, of linear space in general. Okay, not only matrices. Okay, and so let me just show that. So the first exercise of the worksheet is about showing that some stuffs that are applications that are defined are really good, well-defined inner products. Okay, so just hold on. Let me just write the tutorial. So maybe somebody wants to come to the board and try this. So, anyone? Yeah, sure. Thanks. It's the usual stuff we want to show. So, as we saw during class, there are three main properties we need to check. Okay, we need to check that it's bilinear and symmetric and definite positive. All right. And as we said during the lesson, if you show symmetric and linearity just in one of the arguments, you get bilinearity. So. Yes, okay, so that's the definition. We are in Rn of x, so we are dealing with polynomials of degree at most n, and we're defining this product as the sum for two polynomials of their values at integer values. Yes, very good. Yeah.
So it's symmetry.
Yep. Okay, and linearity. So it's as usual, we take two polynomials, we take the real value, and we show the product. basically we're just using the linearity of the sum. Right here. If we take a polynomial, lambda p1 plus p2 at point k is really the sum of lambda p1 of k plus p2 of k, and then we split that sum the same we have. One. Okay, so yeah, linearity symmetry, we get bilinearity and symmetry. Okay, so these two steps are usually pretty easy, but you really have to show exactly what he did. Dot product, scalar product of p with q is equal to the scalar product of q with p. Right, so you can exchange the rules of the two items of the two inputs and the linearity as you. Okay. So again, it's really that if you plug a linear function, you get more precisely exactly what we should write in the end. What you want to obtain in the end is really express that now as lambda inner product of p with q plus that's p1 and p2 with q. Okay, so just as before linearity. You know this is where you begin, you know this is where you end. You have to do the calculations in between to find out the details to prove that. Okay? Yeah. And the hardest part usually is on the definite positive property. Okay? Which tells you that if you plug twice the same argument, you should get something that is positive. Why is that? Because this is what we're going to use to define norms, distances. Okay, so we need that to be positive. Okay, so first part, in the definite positive, we have, well, we could say it's in two parts itself. So we have the positive part, right? So here we've got the sum of squares, so it's positive. And then we need to show that if ever this is equal to 0, so the thing is set, so that's one thing. Both are in the definite positive property. We need to show that if ever you have this equal to 0, you have to show, so that the question mark is on the implication, that it implies that you have the 0 elements of your space. Okay? If ever you apply this definition to some p and itself, and you get 0, we want to show that actually it meant that it was the 0 polynomial. Okay? Again, because this is going to define a norm, and we want the norm to be equal to 0 only for the 0 elements. Yep.
Is it correct?
Sorry?
Is it correct?
Yes, absolutely. If the square is equal to 0, it means that it's equal to 0. Oh, yeah, but this you have to prove. Okay? First of all, for which k are we talking about? I think it's useful here, well, it is useful here to write it for k is equal to 0 to n. All right. Now let's ask ourselves, what does it mean for a polynomial to have a value k such that p of k is equal to 0? How do you call that?
The null function.
No, we're not yet at the null function. How do you call k? I mean, the value k for the polynomial.
And does the roots.
Yeah, it's a root. Yeah. And how many roots do we have here? Yeah. Yes, we have n plus 1 roots. And what's the degree of the polynomial?
N plus 1.
N minus 1. Yeah, we get, so it's a polynomial of degree n with n plus 1 roots. What do you think about this? Poincaré theorem, guys? fundamental theorem of analysis of algebra, sorry. Okay, any polynomial of n of degree n has at most n real roots. Okay, so it means that you can factor your polynomial with x minus the root. If you have n roots, that works. That gives you a polynomial of degree n. Okay? What does it mean if it has more than n roots? What do we want to show?
It belongs to.
It's equal.
It's equal to.
So we're there actually, okay? We've got a polynomial of degree n, but we know that it has at least n plus 1 roots. Okay, so according to the fundamental theorem of algebra, or don't cite the theorem if you're not sure, it means that it must be the zero polynomial, because any polynomial of degree n should have at most n roots. Okay? N real roots. And here we've got n plus 1.
So should I say that the degree of p is 0?
No, the degree of p is n. Well, it's smaller or equal to n. It has n plus 1 roots, so p must be equal to the zero polynomial. Okay, but I agree this one was, you really had to, we're not using that too often. But. Yeah, that's it. Has at least, oh yeah, at least.
I don't understand why the fact that it has n plus 1 root, at least, why does it prove that it's 0?
Okay, p has at least n plus 1 roots. P has degree at most n. Okay, because it's in our analytics, right? Fundamental theorem of algebra, any polynomial of degree n has at most n roots. So if it has more than n roots, the only solution is that it's the zero polynomial. Okay? And so any polynomial of degree n has at most n real roots. Okay? It has exactly n complex roots counting the multiplicities, but when you go to real values, you have at most n of them. Okay? So that's all. We've got more than n, so it must be the only way that this is happening is that if it's the zero polynomial. Okay, great. You had prepared that. No, so good. That's even better. Try to have it today, okay? All right? So, to summarize, the method to show that you've got a well-defined inner product is always the same. You have to prove P product Q is equal to Q product P. Then you have to prove linearity, which is always that thing. If you apply the inner product of one of the items with the linear combination of the others, you get a linear combination of the inner products. Okay, and then definite positive, usually positive part is easy because you get some squares, you get things like this. And the hard part is that one, because that's really going to change every time. Right? The important is that what you want to prove is that if you apply your product to the same argument, and it's equal to 0, then the question is on the implication. It should give you that the only possibility is that your input was the 0 of the space. Okay, so if we are looking at polynomials, it should be the 0 polynomial. Okay? Let's do the second one. Again with polynomials. Anyone? we'll work that together. So what we mean here by the power with some parentheses around, it's the derivative. It's the case derivative at point 0.
Symmetry.
Yeah? So well, the conclusion should be is equal to PQ, so it's symmetric.
You want to see. If you want to see, you want to see.
Yeah, I think there are polynomials in that second one. Yes, there are still polynomials. It's the third one there. Yes? Okay, so linear, symmetry plus linear, we have symmetry plus bilinear. Okay, so then definite positive. Can you stay on the maybe right slide because
Then what I thought is that if we do the derivative, if
first prove that it's positive.
Yes.
That's why is that positive? It's just like before this one, okay? You get p to the k of 0, and then that's times itself, so that's a square. Okay? Okay. As a sum of squares, as a sum of positive values, it has to be positive. Okay, now the hard part is indeed on, do we have that it's the zero polynomial if ever we get that this is equal to 0. No, that's assumption. Question is on the implication. Does it imply that it has to be the zero polynomial? Oh, no.
No.
No. Well, this we can deduce. Of course, if your sum of positive values is equal to 0, it means that each of those positive values is 0. Okay? So here we have, this is sure. The question mark is, does it imply that p is equal to the 0 polynomial?
So it's the same as the question before, because you are-
Similar.
Yes.
No, we don't get that. What does it mean that p to the k of 0 is equal to 0? What does that mean?
That the degree of this will be 0. No,
No.
will be 1. It's not,
No. Okay, so again, p to the k is the kth derivative.
yes.
Yeah, it's the kth derivative
Okay.
of p. Okay, right? So 1k is 0. What does it mean? It means that p of 0 is equal to 0. Okay, so it means that what does it imply? First, for k is equal to 0. Yeah, it has a root. That root is 0. What does it give you for a polynomial that it has a 0 root? Yeah? Yeah. We know that the constant is equal to 0. Okay? Let's now try to understand what does it mean if first derivative in 0 is equal to 0. Okay, that's what we would get if we take p to the 1, so that's p prime of 0 is equal to 0. What does it imply?
It's the slope at p equals 0.
Yeah.
Is 0. Right?
Yeah. Yeah, sure, that's, yeah.
But that doesn't prove that the p equals 0 has to be a root. It could be like at 5, for example.
Okay. All right. Let's say,
I just don't know how you, like, you know p of 0 is equal to 0, but I don't know how you go back each step and still.
it's acquired. I mean, we know that for every k, this is true. Okay? So what we obtain for k is equal to 0, for k is equal to 0, we know that p of 0 is equal to 0. What does it mean? It means that we have no constant in the polynomial. Okay? Or the constant is equal to 0. What we can do, in any case, if you need to define things more clearly, we can say that if p belongs to or n of x, we know how to write it. Yes, it should be a polynomial, a0, a1x, a2x2, etc., up to a(n)xn. Okay? a0 plus a1x, a2x2, etc. Right? That's any polynomial of degree at most n will be written like this. What we got for k equal to 0 was that a0 was 0. What we want to get is that, well, it's the 0 polynomial, meaning that all the coefficients should be 0. Okay, so what do you get from p prime is equal to 0? P prime of 0 is equal to 0.
P would be a1x plus a0, so a0 equals to 0. Okay.
We already have a0.
So
Write p prime of x, write what we get. If you say, well, that's the notation I'm going to use for p, then first derivative,
okay, so a1 will be equal to 0,
yes.
and etc. All the
Yeah.
values will be-
For each of the k, when you get that p, the kth derivative of p at 0 is equal to 0, you get that coefficient ak is equal to 0.
So how can I write it?
Well, you,
Yes.
in a sentence, it should be a mathematical sentence. what we can write is that p to the k of x is going to be, so what do we get? K minus 1, well, we get factorial of k, times ak plus whatever happens afterwards. Whatever happens afterwards is just that for the next one, you will have k plus 1 times k, etc. It starts at 1 of ak plus 1 x. And the last one would be, so n minus 1, I go n minus k, and that would be xn minus k. Right? That's what it means to make the derivative. Okay? But in any case, what we can write, if it's complicated for you to write this thing, what you can write is that the value at 0 is just going to be k factorial ak. Right? This one you can compute it by just trying the first ones and then infer it, do some kind of induction, right? But this is something, this is where the Taylor formula comes from, okay? Right? So you can write this, so what do we get? If that's equal to 0, then ak is equal to 0. Yeah. Okay, and so if ak is equal to 0 for all k from 0 to n, it means that p is equal to the 0 polynomial. Only because of its coefficients are equal to 0. Just to be sure we understand how to manipulate these formulas. Well, first, do you need more explanation on that? Okay? When you are not sure what it means, you should try to apply the formula. Okay? You should try to apply the formula. If I tell you that I'm looking at polynomial and for simple values, so let's say we are in O2 of x, we've got polynomial of degree at most 2, so it's not too simple, not too complicated, it's things you can manipulate. If you've got p of x is equal to a0, a1x, a2, x2. What would you get? What would you get for p with itself? Which then will be written, as we proved, it was a well-defined inner product. That's going to be the norm that I can define of p in that space. So what will we get? Calculate it. just apply the formula, okay? That's going to be the sum from k is equal to 0 up to, well, 2, right? If I go further, to just give me 0 anyway, of, so we get, well, pk of 0 squared. Okay, so we have to compute that. Right, so we need for p, well, not derivatives, for k is equal to 0, so p of 0. We need p prime of 0, that will be p1 of 0, and we need p second of 0. Right? So p of 0, this is going to be 0. So we get first a0 squared, then p prime of 0, differentiate your polynomial. So we get a1, right? So a1. And next one. Yeah. Okay. Next one will give us. So if I differentiate once, I get a1 plus 2 a2x. If I differentiate it one more time, I just get 2a2. Okay. So the next item will be 4a2 squared. Okay, and so if you try it on one example, simple like this, you see that, well, that implies that if this is equal to 0, then it implies that it's equal to a0 should be equal to 0, a1 should be equal to 0, and a2 should be equal to 0. Okay, so we have the node polynomial, right? And then you can infer maybe some formula, so which would be that the k's derivative is the factorial of k 8. Okay, that's. I don't think I would ask you directly to invent, well, to find that by yourself in a test. I would probably guide you for this. Yeah.
Could we have, sorry, that's to prove that p of x equal to 0, if only if p is in the.
What?
Could we have used that p squared is equal to the inner product to prove that it's another polynomial?
Well, we get that it's a non-polynomial because if this sum is equal to 0, it means that all items are equal to 0, and if all items is equal to 0, it means that we have the non-polynomial.
Yeah, but I mean, could we have do that? Would be an sufficient proof to use?
Well, you need to. If you do it on a second order polynomial, that's clear that it implies that a0 is 0, a1 is 0, a2 is 0. If you do on any degree n polynomial, there must be a proof at some point. Okay? It's just so if you expand that with the degree n polynomial, you will get something like, well, a0 square, a1 square, 4a2 square, and the generic term would be factorial of k square, ak square. But you have to exhibit this value, right? Otherwise, we can't know that it will imply that the ak is equal to 0. Okay? So there should be some justification, yes, at some point. Right? And that's the part that is going to be different for each definition of the inner product that you are given. Okay? Right. Next one, now we're with functions. Generic functions. So anyone? So now it's, okay. Okay, it's easier, I think, the next one. So somebody for that. That's right.
There's a bed and
There is what?
there's a bed and thing.
Okay. Okay. It's 1 minus t squared, but what?
Oh, it's 1, sorry,
It's
yeah.
1 minus t squared, and the square is out of. And we don't need any, sorry.
Oh, yeah, obviously.
Yeah.
I was,
Okay, here it's just we define the scalar product of those two functions like integral of that product times some 1 minus t squared function. Okay, these kind of things may seem to you very abstract, but actually there are some applications of this, of course, because it's math, but all the linear algebra, when we're dealing with spaces of functions, for instance, that's something that would be used in signal processing. Okay, how do you define, how can you find basis for some song, for some sound signal, or for some visual signal? That's one of the applications. And then the fact that we can define distances for this to define whether, for instance, a sound is close or far from another sound, we need to have an inner product. Okay? And something like this would maybe tell you that, okay, I'm doing some inner product, but if I multiply by this kind of weight of function, it means that I'm giving more importance to what's happening when this is important, so around the 0 point. Okay, so these all seem maybe for you very abstract, but it has a lot of very important applications. And in statistics too, we can use this kind of definitions. Okay, here even better, we can put the lambda out of the integral, because what we want in the end is really this one, right? And it's even better if you just justify by linearity of the integral. Okay, in the end we always use linearity of things that we know are trivially linear. Okay, then we get, no, not.
No.
No. You see, I just wrote twice f, so f, and I just get this one.
Oh, yeah, okay.
Okay. So you've got one too many here. This one. Okay, so I've got f squared times 1 minus t squared.
And so,
So first, is that positive? Yeah. Yeah.
The square is on the T only.
oh, est-ce que le faire?
Oh, it's inside. Okay, yeah, thanks.
Okay, and so,
So why is that positive?
square.
Yes, yeah, sure. The square makes a positive function. Then 1 minus t squared between negative 1 and 1. Is that positive? Yeah, sure. If t belongs to if you're not sure, try it. T belongs to negative 1, 1. If you square it, it's going to be between 0 and 1. Oh, we should put large ones. And 1 minus t squared, then it's going to be
Between 0 and 0.
no, between 0 and 1. Yeah. Or,
Yes, yes.
so if we so minus t squared is going to be between negative 1 and 0. 1 minus t squared is going to be between 1 and 0. Okay? Important thing is it's always positive or equal to 0. Okay, so we get the integral of some function that is greater or equal to 0. What does it imply?
F of t is positive.
What?
So, you just say directly that f of t is positive?
No, I don't know about f. F could be anything. That's the idea. When you want to show those properties for any f in the space. So it could be negative, it could be whatever, right? But then if you apply f twice for this inner product, you get this interval. Do we have that this is greater or equal to 0? First question. Then we'll see about equal to 0.
Yes.
Yeah, yes, sure. That's why.
I'm trying to imagine it in my head and it's not working.
Okay. So keyword is positivity of the integral. But what does it mean? What does it mean to take the integral of something? So let's say that f squared times 1 minus t squared, we said between negative 1 and 1. It's something, it's a function. Obviously, in negative 1 and 1, it's going to be 0. Okay, because if t is equal to negative 1 and 1, t squared is equal to 1, so this cancels. And so in between, I've got something that does whatever it does, but I know that it's positive. Okay? So what does the integral of that function, so let's say that this function is f squared of t times 1 minus t squared. What does it mean to take this in the integral of this function on that interval? What does it represent? Yeah? What? Yeah. So the integral of a positive function is the area below the curve. Okay, so taking the integral of that function, that's calculation of that area. Right? So it's going to be positive. If your function is positive, well, you know that you can interpret integral as signed area. So if your function is positive, your integral is positive. That's all. Right? So we get that it's greater or equal to 0. And you don't need to justify this, just say by positivity of the integral. That's one of the basic properties of integral. Yeah? But in the end, if you want to understand this property, it's really related to the fact that it's a calculation of an area. right? Same thing, if it's equal to 0, what does it mean? Same justification. By positive of the interval, if your area below your curve, and you know that your curve is positive is equal to 0, it has to be the flat function. It has to be a function that is always 0. Okay? Again, same justification by positivities of the interval. So, do we have, no, the question was, do we have that this is very equal to 0? Okay, so same justification. If this is equal to 0, that means that what's inside of your integral, because it was positive, and by positivity of the integral, it implies that, okay, no, stay here. This is equal to 0, okay, for all t. All right? This, there is no more justification than saying that it's the positivity of the interval. But what we should conclude from that to get positive definite is that f is equal to 0 for all t between -1 and 1. Because the 0 of my space being the C1, the C function, are the functions that are defined between -1 and 1 and that are continuous. So I should prove that it's the 0 function on that interval.
Prove that.
So the question here is, does it imply that f of t is equal to 0 for all t between -1 and 1? Because in the definition of my space, it's closed. So what do you think about this? I've got a product that I know is equal to 0.
I see it in my head, but I don't know how to geometrically I see it in my head, but I don't know how to prove it.
Okay, or let me write this here. What we know is that f square of t, so we know that for all t between -1 and 1, f square of t times 1 minus t square is equal to 0. What we want to conclude is that f of t is equal to 0 for all t in -1, 1. Why? Because this is the 0 element of the space of continuous function between -1 and 1.
So first, when you say that, because 1 minus t changes, can you just take out the equation and only focus on the f squared t?
Sure, it changes, but it remains. Okay, write what you wanted to say. To write.
I wanted to say that since this isn't equal to 0.
Well, it might be.
Well, not everywhere.
No, not everywhere, sure. But we get even more information. What we used earlier. It's not equal to 0, but even it's positive. Okay. Well, don't worry, we can need that. Yes, you're right. So it's not equal to 0, but it is equal to 0 at some values. But yes, you're on the right track.
So then you can just say that f squared t is equal to 0.
Yeah.
And so because of that, the function squared
Don't even think in terms of function. You've got the square of the value equal to 0 and this is okay? Okay, reasoning is correct except for some values. Can you just right? Reasoning is, we know that this is our assumption that product is equal to 0. What he said was, well, that's different from 0, so if I've got the product equal to 0, it means that the other term is equal to 0. So f squared is equal to 0, so f of t is equal to 0. What's missing here? It's nearly complete, yeah?
He didn't precise the interval.
Yeah? When you write that this is different from 0, for which values, I don't agree. This might be 0. We are looking at t between -1 and 1 included.
I'm talking about the integral of the 1 minus t squared isn't equal to 0.
Yeah? Yeah, that's our assumption. Okay, the reasoning was the following. We had that if we applied f twice, we had that f square of t times 1 minus t square was greater or equal to 0, of course, and then what we say is assume it's equal to 0. We take the hypothesis it's equal to 0. What we want to prove is that it meant that it was the 0 function that we plugged in. Okay? That's what we were saying. So we started from that. Next step was to say, well, if the integral of the positive function is equal to 0, by positivity of the integral, I know that the function inside was 0. Okay? Right? Function inside was 0. So from that, again, we need to prove that it means that f of t is equal to 0. Your argument was to say, well, this is different from 0, so it means that f square of t should be 0, so f of t should be 0. But I don't agree on that. 1 minus t squared, it's not different from 0 everywhere, especially on that interval.
But you need to prove it on the interval, on the whole interval, so like the one point where it works doesn't really matter, does it? See what I'm saying? Like, yes, like at t equal 1 and minus 1, like it's equal to 0, but since you're proving it on the whole interval, then you don't really care about it.
Yes, we do. Okay? But there's something interesting here. So there's something slightly wrong in what I've written here. What is wrong is that if your integral of your function is equal to 0, it means that what's inside is equal to 0 on the open interval. Okay, if I use those notations, right? Because you know that it doesn't change the fact that you're doing on open or closed interval in terms of integrals, because again, if you consider that this is an area, the fact that you've got some value at just one point isn't important. More about this next year. But if it's just on the borders of the interval, it doesn't change whether you're really staying with some values or just at those points taking some different values. So technically, from that, we get that, and if we exclude -1, 1, I agree, then it's different from 0, right? And so we get that. So what do we get from that? For all t between -1 and 1, f of t is equal to 0. But that's not enough to prove that. What's missing here? We miss the fact that f of t is also equal to 0 at the border, right? Because we are in series of -1, 1 included. So how can we conclude that? So we have that inside here, my function is equal to 0. Could it have any other values at the border? If I was considering any function, yes, but I'm not considering any kind of function.
Other.
Yes. Yes, we're considering continuous functions. Okay? So if you have a continuous function that is constantly equal to 0, it has to be also equal to 0 at the border, at the boundary of your interval. Yeah? By continuity. But as f is continuous, we have that f of -1 is equal to f of 1 is equal to 0. Okay, because if I take any sequence in that interval, the value of f of 1 should be the limit of f of xn as xn tends to 1. And if f of xn is always equal to 0, because for any item inside it's equal to 0, then of course at the limit it should be 0. Okay? Yeah. Thanks.
Yeah, thank you.
quickly one last one. Or should I leave that one for you to work? Yeah, I think I'm going to leave that one for you to work. Ask me questions on the chat, okay? Try the last one by yourself and ask me to check if it's correct, right? And next one I would like to do is the exercise 6. Okay, and we will deal with the other ones after the exercise 6. Okay, so we're doing Gram-Schmidt again, right? Things we saw during first semester. It's a very important process because it allows you to create orthonormal bases out of any basis. Okay, and that's very interesting because when you've got things that are orthogonal, it's much easier to work with them. Okay, so who's coming for that one? Okay, so the inner product that we're considering here is just the dot product, and this is it.
A little bit, like the end of the process.
Okay, let's do it. Let's find it again. Yeah, sure. Okay, how does it work? We've got 3 elements here. They make a basis of all 3 in our case, and we want to build the rectified one. Okay, we want to build E1, E2, E3. Again, the idea behind the process is take the first one, we norm it, take the second one, we subtract from the second one whatever belonged to the first direction, we norm it, and then for the third one, we take the third one, subtract whatever belonged to the first and second direction, and norm it. Okay? Let's do it. Right, so first one. So my basis is 1, 1, 0, 1, 0, 1, and 1, 1, 1. That's the U. Well, usually the E letter for the basis items are for the nice ones, but that is just notations. That's, well, U1 is okay, your first one, but then it's not normed, so you have to norm it.
Yeah. So it's 1 over
Yeah,
U1.
yeah. Yep. Okay, so we have 1.
It's U2.
Yep.
So
Well, you've got the 1 over square root of 2 as a factor.
but I still have, this is not my lambda.
No, that's not your lambda, but your vector E1 is really 1 over square root. Do you remember how we find lambda?
And then there's E2 is E1.
Yes.
The dot product.
Yeah.
So lambda should be something.
Yes.
So
Exactly. Yeah.
E2 dot E1 0.
Write it in general. What do we get when we get E2? So we start from that. You define, well, that's E2 prime technically because E2 will be the wrong version. E2 prime is equal to U2 minus lambda E1. And then you use E2 prime dot product with E1 is equal to 0. What?
What's the
Okay, don't use the specific values we have because this is something we're going to prove. Okay, so you have those two things. E2 prime is equal to, as we said, we take Q2 and we subtract something times E1. Okay, so you've got your E1 vector, that's your U2 vector. What you want to subtract is its projection on E1 in order to keep only what's going to be not redundant as in terms of information. Okay, that's the idea behind that. Okay, and so you know this, and you also know that E2 prime dot product E1 is equal to 0. So, if you know that, if you know something about the dot product, apply the dot product with E1 to that first line. What do you get?
So that's this thing. Yeah.
Yeah, you get E2 prime dot product with E1 is equal to 0. Yeah, okay. Yeah, sure. Okay, on the other hand, we've got that's equal to, we said E1 dot product E2 prime, yeah, sure. And of course, we started by saying that this should be 0. So you get 0, and you're looking for lambda.
Are E1 and E2 ordinary?
No, no, not yet. But we know that the product of E1 with itself, we know it.
Yeah,
One.
so it's 1.
It's 1. So what is lambda?
It's 1.
No.
It's, this is,
So you're looking for lambda.
yeah,
Lambda is equal to,
it's thing.
Yeah. That's it. Okay, so yeah, that's it. And that's what we said. This dot product gives you, if you remember in the plane, if you reason with the plane, because this is something we can picture, the dot product of the two vectors is the magnitude of each vector times the cosine of the angle. Okay, so this is what we get. If we get that one of the vectors, well, that's just going to give you the orthogonal projection of U2 on E1. Okay, that's really product of the magnitude, knowing that one of them is equal to 1 because that's what we built. And so we get just the magnitude of E2 times the cosine of this angle, right? So that we can subtract this thing. This value if we multiply it by 1. Okay, so maybe I can sum that up. So we get E1, which is equal to 1 over norm of U1, then we build E2 prime by saying that it's U2 minus the lambda we found, which is dot product of U2 with E1 times E1. Okay, basically that's the formula we obtain. And then U norm E2 prime, and that's going to be your E2 vector. Okay, and then next one is going to be E3 prime is U3 minus projection on each of the previous ones. Okay, so minus U3 E1 E1 minus U3, E2, E2. Okay, and if you had a fourth vector, if you were in dimension 4, you would do the same thing, add the next one, and subtracting each time the vector you have. Okay, so where are we now? Okay, yeah, sure, right? So 1 over square root of 2 times 1 over square root of 2 times 1 1 times this vector. So what do we get in the end? Maybe we should erase things. It's going to be a bit. It's beginning to be a bit messy here.
Is that true for lambda?
Yeah.
Why is it negative?
You can work with negative or positive values, whatever. Okay, it's just that in the end this is the formula you get, but when you're looking for the lambda, you can write it with positive or with negative value. Okay, hold on. Before you go on, we should write what we have, right? So we have what we can observe, right? What we can observe every time. So that's your input prime. It's going to be your U2 minus lambda times your E1. And your lambda is going to be U2, E1, E1. Okay? It happens that E1 is your 1 over square root of 2 times your vector 1, 1, 0. Can you just move up to the side? 1 over square root of 2 to vector 1, 1, 0. What I want to show you is that you don't have to really care about those square roots, because every time you've got the norm here, okay? It means that you can factor with the norm square. So it makes the calculations a bit easier, right? So in the end, what we have is that we have U2 minus 1 over 2, dot product of U2 with this vector times this vector. Okay, just if you want to go a bit faster, don't want to mess up with the square roots, right? And so dot product of U2 with 1, 1, 0, just 1. Okay. So you get 1, 0, 1 minus 1 over 2, yeah, times 1, 1, 0. Yeah. Yeah, that's it. That's it, fine. Yep.
So is it the norm of E2 prime?
Yes, sure.
So it's the square root of 1 and 2 square root of 3?
No, it's square root of, yeah, plus 1 over 4, plus 1 over 4, plus 1. Yep. Okay. Last one. Is that okay? I mean, this thing is just, when you get used, you see that you always have, if you have a norm vector, you have a vector times divided by its norm, okay? And if you divide by its norm here and by its norm here, it means that you can factor with the norm square, which usually makes the calculation easier. then you can use directly the definition. Okay, so once you're here, you can use directly that it's going to be U3 minus U3 E1 E1 minus U3 E2 E2. Don't redo the whole reasoning.
Okay.
You've done it. It's all right. You can use that directly. Right, because in itself, it's already showing the understanding of the formula. So E1, we said, we erase that. So 1, 1, 0, and you've got the 1 over square root of 2. Okay, you still have 1 over square root of 2 as a factor for both lessons. So yeah, you've got the 1 over 2 as a factor. Good. So 1 on 1. The U2 we found was that one. One half, negative 1 half 1. Yes.
One plus one, two.
Yep.
One second.
That's good. Very good. Yeah. Well, we get square root of 3 over 2.
Oh, no, sorry. And we squared.
Yeah. Yeah, but can't you answer that already?
That's it's a 2.
I mean, yeah, you can take as many steps as you like, but when you've got the square root that is squared, just go directly for it.
So that's 1 plus 1 over 2 minus 1 over 2 plus 1 plus 1.
Yep. Yep. I guess just simplify the 2 over 6 as 1/3. And finally, what do you have to do on that? Let me check. I think it's alright. Okay, let's check the results. Maybe. You need 1/3, 1/3, and 2/3.
The last row is that.
With the, yeah, with, it's 1/3, the last one. It's 1 minus 2/3, so it's 1/3, the last one. Okay, and the last thing we have to do,
meters.
Yep. So we just need to norm it in the end. What?
I think that the change in my mind is
Right. Square of 1/12.
because it's 1 over 9 plus 1 over 9, so this is 3 over 9. So this is okay.
Yes. Okay, good. Slightly simplify it, but it's okay. That I'm going to go on. Right, you can just slightly simplify it because that's square root of 3 over 3, so that's 1 over square root of 3. You get 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. Maybe I can write this. Okay, so let me write the result in the end. So that was our starting base. We then obtained that our orthonormal basis is now going to be given by so 1, 0. Then we obtained second one, which was I lost it. Square root of 2 over 3 times 1/2 negative 1/2 1. Which could probably be simplified as 1 over square root of 6 minus 1 over square root of 6. Anyway, and the last one being 1 over square root of 3 times negative 1, 1, 1. That's nice. Okay, we can just slightly simplify this one with this. The last one, I'm just simplifying with the, so that makes square root of 3 times 1 over 3, so 1 over square root of 3. Okay, right. I wanted to do with that exercise. Remind you the Gram-Schmidt process because we're going to do Gram-Schmidt with polynomials next time. Okay, that's the idea. Oh yeah. What's so good about orthonormal basis is also the fact that then it's very easy to express anything in an orthonormal basis. Right? So the next question is find the coordinates of some vector, which happens to be 1, 2, 3, whatever it is, okay? So this is the coordinates of a vector in the Cartesian basis. Now I say, I want the coordinates of this same vector, but in that basis. Previously, what would you do to get this? You would do the change of basis formula. Okay, which I remind you is that x is equal to px prime, right? You're looking for x prime, you have, this is the x we have, and we write it this way because the p we directly have because that's the matrix that contains these vectors as columns, right? So if you wanted to find x prime, you should write p minus 1 times x, meaning you have to compute p minus 1. We'll see later that when the columns are orthonormal, it's very easy to compute. But in any case, we're not going to use that because we've got an orthonormal basis and we know it. What does it mean? It means that anything, or let's call that V, can be expressed in that basis, right? It means that it has some V1 coordinate times E1 plus V2 coordinates times E2 plus V3 coordinates times E3. And I'm looking for these V1, V2, V3, these components, right? What's happening is that let's try to apply scalar product and inner product with any of those basis vectors. Okay? So what I'm going to do is apply that inner product on both sides. Okay, I'm taking that and I'm going to apply it to E1, for instance. Okay, so what's happening? Expand that by the linearity of the inner product. So we know we're going to split that into those three parts, V1, E1, E1. That's one part of the linearity, yeah?
And the rest goes.
That's what's going to happen, yeah, right? And then by linearity, I can also extract the coefficient that's a real coefficient. So that's also equal to V1, E1, E1, plus V2, E2, E1, plus V3, E3, E1. And this is where the magic happens because we've got an orthonormal basis. Because we've got an orthonormal basis, I know that E1 is orthogonal to E2 and E3, so these are just 0. And E1, E1, because it's a norm basis, that's the norm of E1, that's 1. Okay, so that's what's very nice also about orthonormal basis, is that if you're looking for the components, for the coordinates in that basis, you just need to apply the inner product that you have. Okay, so in general, so we get this result in R3, but this is completely general to the fact that we have an orthonormal basis. If we've got that X is the sum of Xi EI in some basis, so let's say from I equal 1 to n, if E1 up to En is a basis of your space, of linear space, so it means that anything can be written as a linear combination of the basis items, and we get that the Xi component or the Xk component is just going to be given exactly by applying the same process by the inner product of X with the Ek vector of the basis. Right? Okay, so that's important. And that's in the end, that makes it very simple. Right? Once you have your orthonormal basis, you've got this very simple relation. Right? So that if I want to get my 1, 2, 3 vector in that basis, I just have to make 1, 2, 3 dot product with this one, and then 1, 2, 3 dot product with the second one, 1, 2, 3 dot product with the third one. Right? So so if I say V prime is the coordinates in my new basis, in my E1, E2, E3, I get that the coordinates are going to be given by V E1, V E2, V E3. Okay, and so V1 is 1 over square root of 2 times 1 times 3. Yeah, times 3, and then I've got the second one that's going to be square root of 2 over square root of 3 times 1 times 1/2 minus 1/2 plus 3 minus 1/2, that's 5 over 2. So that's 5 over 2. Yes, square root of 3. Yep, that's it. and so on. So the next one will be 1 over square root of 3 times 1 plus 3, that's 4. That's 4 over square root of 3. Okay, and you can check, of course, if you like, that if you take square root of 3, 3 over square root of 2 times that vector plus 5 over square root of 6 times the second vector plus 4 over square root of 3 times the third one, you get the vector 1 plus 3. Okay, so if you like, you really can check that. Okay, so that was just as a very important illustrative example. Right? Once you have also normalized your basis, you can get very simple results like this. Okay, without going through all the process of the P matrix and the bucket. Okay, good. So let's go for which one? Okay, quickly the second one and third one I will try. Well, let's try that again. So Cauchy-Schwarz inequality, very important one, tells you that when you've got a well-defined inner product, you get that this is smaller or equal to norm of x, norm of y. Okay, norm of x being the square root of inner product of x with, okay, that's a very important one. And it works with any kind of inner product, right? Two things about this. One thing is that you've got an equality in which case, most of the time we get a strict inequality, but do we get an equality in some cases?
Yes.
Yeah?
If they are collinear.
Yes, very good. If x and y are collinear, okay, right? So you've got quite a lot of things on Cauchy-Schwarz inequality in the lesson, right? Including the proof, which is always useful. That's one important thing. That's what we're going to use in that one, okay? And the other thing is, I usually give also this inequality in year one just for the functions. When we've got this definition, a very classical inner product. Okay? Classical inner product is that one we get on some domain. Okay. The integral of a product of functions, right? That's a very classical way to define an inner product. It's a very famous one. It's the most important one in when we're dealing with single processing, for instance. Right? That's what will give you the Fourier transform and the Fourier series, if ever you've heard of those things. Right? So that's a very important one. But what's important is that in year one we do a lot of integration, and we get a lot of things like this where you will have the integral of a product. And many times, as students that are really tempted to write that the integral of the product is equal to the product of the integral, which of course is completely wrong. Okay? So, but what do we know about the integral of a product? We know that we're going to have, well, usually we write this with a square so that we don't get square roots everywhere. That is going to be smaller or equal to the integral of the square, the product of the squares. Okay, so that's why sometimes when I teach tier one, I would give that inequality in year one, so that I would never see anything related to the integral of a product that wouldn't be correct. Okay, so just as a side note. All right, Cauchy-Schwarz. So we're going to use that. Let's do the first one. Exercise 2. We've got x1 plus x2 plus xn is equal to n. And we also know that x1 squared plus x2 squared plus xn squared is also equal to it. And we want to find what are those xi. Okay, using Cauchy-Schwarz. What does it mean? It means, well, the hint that you have to use this inequality, or this, in that case, equality, it means that we will have to identify some inner products. Okay, so we are in our N. How can I identify those inner products? This one is pretty clear. What do we have? How can I interpret this in terms of an inner product? It's the norm. Yeah, that's really the norm of x squared x with itself. So let's denote x is equal to that x1 up to xn. This is what we're looking at. Right? So we have that norm of x, so x with itself, that's equal to x. How can I interpret the first one in terms of an inner product? What kind of inner product could that be? Yes?
The square root, the norm of the square root.
It's not a norm. I want us to interpret this as an inner product. That could be the inner product of x with what? Yes, with a vector that only has ones as components, right? So the first one tells you that x with the one vector is also equal to it. Okay, so if I denote the one vector here as the vector that only has ones as components. Okay, so we've got these two things, these two facts. So let me write it here. Well, I can write this in terms of norm. So norm of x squared is equal to n. Norm of x is equal to square root of. And I also have that x1 vector 1 is equal to n. Okay, so what can you think of? Knowing that you have to use this famous inequality. Yes? Okay, so by Cauchy-Schwarz, that should be smaller or equal to norm of x, norm of 1. So norm of x, we already know it's square root of n. What's the norm of the one vector?
Oh, so it's
It has ones everywhere.
one of the square root of n.
Let's write it. Norm of the one vector,
No, one of the
it's 1 square, well, so the square root of 1 square plus 1 square, etc. That's just the usual dot product, okay? So what do I get in the end? Square root of n. Alright? Right, so that's also square root of n. So I should have that square product of x and 1 should be smaller or equal to norm of n times norm of n. It makes n. But I don't have an inequality. if I apply Cauchy-Schwarz inequality, I should have this x1 smaller or equal to n. But we have that it's equal actually. Yes?
So what you wrote, it's equality to collinear.
Yes? So x is collinear to 1. Next, we need to find the collinearity coefficient. So we know, as we have an equality, x is some coefficient times the vector 1. So we need to find this coefficient. So I know that actually x is the vector that contains k, whatever. Well, the same value for each component.
Didn't you just calculate the norm, so therefore they're the same? They have the same norm?
Yeah.
So k is equal to 1.
Yes, exactly. Yeah, sure. Excellent. All right. The other information we have is that actually the norm of x is square root of n. And if we take the norm of this vector, we're going to have square root of k times n, right? So we must have k. So k squared times n. All right, good. X is equal to square root of k squared times n, k times square root of n. We should have absolute value of k. But then we find that k is equal to 1. As we know that norm of x is square root of n. Okay, it wouldn't be negative 1 because otherwise we wouldn't have then it's equal to plus 1. So it must be plus 1. Okay? Right, so that's just a very small exercise just to use that inequality. Next one. Next one, so we are in an Euclidean space. So Euclidean space is a finite dimensional space with an inner product. So when it's Euclidean, you know that it's finite dimension, but whatever. Right. So I'm not sure it's important. We want to show that x and y are orthogonal if and only if we have x plus lambda y norm greater or equal to x for all lambda. Okay, so we've got first remark, this is an equivalence. So when you have an equivalence, it means that you have two things to show, the two ways of the implication. You have to show that if x and y are orthogonal, then we have this inequality, and we have to show the other way around. If ever we have this inequality, then it must be that they are orthogonal. Okay? Usually one direction is simple. So let's assume that it's orthogonal, right? So we assume that x is orthogonal to y. You know that when we've got our Euclidean space, what does it imply? What does it mean? How do we define orthogonality? Inner product is 0. Okay? So that means that I know that, so this is a given fact, that their inner product is 0. Okay? So that's assumption. So we want to show something on the norm of x plus lambda y. So let's compute that. Okay, so norm of x plus lambda y, well, we'll do the square of the norm and we'll see if we need to square that. X plus lambda 1. Anyone wants to come and expand that? That's the interesting part. So what I just want us to do is to expand this using the bilinearity of the product. Yes?
And then I could check, like, I have 14, so
You've got all the terms to, yes, that's.
do we know if it's symmetric?
Oh yes, it's a well-defined inner product.
Okay.
So we've got an Euclidean space, so we know that it has a well-defined inner product. And this is what's helping us, what's giving us the definition of orthogonality. So you just have to do the whole, the whole stuff.
Since we know it's symmetric, we can just add like those two and plus two.
Yes.
And
Yeah.
it's
Just hold on. There's something that I don't understand. No. Why do you get two more terms?
because I developed these parts and I thought we had also to develop.
Not yet. Yeah, sure. Hold on. So yeah, erase that. You have to know which property you use at each time. Okay? When you split that one into those two parts, you're using linearity with respect to the first variable. Okay, so that's one thing. Go on. Well, one more thing we can do, just very simply, is just put the lambda in. Now, to expand those, we're going to use linearity with respect to the second variable. Okay?
So then I do that.
So if you use linearity with respect to the second variable, each of those is going to give you two more inner product. No. What's the second one? It's not a plus something. Get x with lambda 1.
With some.
Yeah. Okay. One more thing we can do is take the lambda out. Okay, so train on these kind of expressions. It's very common to get them. Yes. So now let's just rewrite this with the norms. X and x, that's x, the square is out of the norm.
And for those two, can I use sign too?
Yes, yes, of course, yeah. Okay. So at first, let me just rewrite what we were computing. That was norm of x plus lambda y squared.
Also, it just
So so that's always going to be true. Here we haven't used anything particular. Okay? But what we know is that we took the assumption that x and y were perpendicular.
so this one is equal to 0.
Yep. So that disappears. Okay, so why is that helping us proving that? Do we have that the norm of x plus lambda y is greater or equal to the norm of x?
So we can suppose this. Okay.
Yeah, with the square,
Yes.
because that's always greater or equal to 0. And so if we take the square root on both sides, it keeps the inequality to the square root is increasing, and so we have it. Okay, so thanks. I will do the second part. Thank you very much. Right, so we get that x plus lambda y square greater or equal to norm of x squared. So we have what we wanted to show. X plus lambda y greater or equal to norm of x. Okay, everything being positive and square root. Okay? Very quickly, the second part, I'm going to work on that. So second part is the reverse implication. So we have, so second part is we assume x plus lambda y is greater than norm of x. What we had obtained, what was always true, is norm of x plus lambda y squared is equal to norm of x squared plus 2 lambda xy plus lambda squared y squared. Okay, so how can I relate? So this is always true, this is our assumption, and we want to prove that it implies that this is equal to 0. Alright, let's do that. How can I relate to that? It's just this. I can also say that that's going to be true for the square. That's going to make this one minus x squared. So I can rewrite this as x minus lambda y squared minus x squared greater or equal to 0. Okay? All right. And then, so that means that this thing, this part, is greater or equal to 0. Okay, and then it's a kind of a trick that is used, for instance, in the Cauchy-Schwarz proof. That is true for all lambda. So we can consider this as a polynomial in lambda. Okay, because I've got some lambda and I've got some lambda squared. And so it's always positive. Right? What does it mean for a polynomial to be always of the same sign?
No, it
that it has no roots. Okay? So if I take the determinant, it should be smaller or equal to 0. Okay, and so what's the determinant of this polynomial? B squared minus 4ac, so 4 lambda square xy smaller or equal to 0. Okay, but what else do we know? How can I conclude now that it will imply that actually, oh, sorry. So it's not, I forgot the square, and that's it. B squared minus 4ac. Yeah?
Why is the lambda indeterminate? What was the...
Lambda shouldn't be indeterminate, you're right. So, 4 xy squared smaller or equal to 0. So what can we conclude? Can that be negative? No, it's just squares. So it can't be negative, so it has to be equal to 0. Okay, so it must be equal to 0. And then we get that they are orthogonal. Well, I use the delta, but probably we could go simpler by factoring by lambda. Yeah.
Why is B squared 0?
Because, well, I guess I didn't need the polynomial. B squared minus 4ac, okay, and a is y squared, but c is equal to 0. So that's my delta. Okay, yeah. Right, and probably I could have factored with lambda and get, yeah. If I factor with lambda, I could also conclude the same way, yeah.
Why is the delta smaller?
Okay. The reasoning. This, I can consider that as a polynomial in lambda. Okay, that's p of lambda. And it happens that my p of lambda always has a constant sign, right? If something has, if a polynomial of degree 2 has a constant sign, it means that it has at most one root, which happens to be 0 for us, because then it must not cross the axis. Right. My root is in 0, so it should be something like this, all right? It must not cross the axis, so it has, because it doesn't change sign, so the delta should be smaller or equal to 0. We compute the delta, we get b2 minus 4ac, the b being 2 inner product of x with y, minus 4 times, 0 for the c, and a is that. So that's my delta for square inner product of x with y squared, b squared. So that should be smaller or equal to 0, so it means that as this is a square, it can't be smaller than 0, so it must be equal to 0. Right, and that's it. Once we get that, it means that they are orthogonal. Okay? This is it. So we have the following of the lesson. Next part of the lesson on Tuesday.
No, are you going to do number 4 and 5 with other classes?
What?
Are you going to do number 4 and 5?
They were, Mr. Owen did them yesterday, and I don't think he had time to do it. But try them. They are not typical in the sense these are not really the kind of things that I'm asking you, I guess. But try to do them however, right?